something. All right, so let's start now with the reactions of our carboxylic acids. Let me join the group, the chat real quick with my phone so I can see the chat. You get me? So I can answer questions and stuff like that. And please be responsive, right? We're gonna be answering some questions, right? Okay, so Joel's here. All right, so let's just start now. Okay, reactions of carboxylic acids, right? So throughout this entire I guess lecture, we're gonna be describing selected reactions of carboxylic acids with sodium hydroxide, sodium hydrogen carbonate, and metals. Magnesium we're gonna be looking at, all right? Okay. Describe the reaction of carboxylic acid with alcohols, which is esterification, right? Then describe the reactions of carboxylic acids with phosphorus 3 chloride. And that, what does the 3 entail? Not sure if you guys remember what the 3 means, from Unit 1 chemistry, but I hope you know. Phosphorus 5 chloride, as well as sulfur dichloride oxide, or what we call thionyl chloride, okay? The carboxylic acid. Have you guys seen this before? You guys have seen this before, yes?
Yes, sir.
All right, we're comfortable with it?
I am.
You're like, you are, you don't know about nobody else, but you are comfortable with it. All right. So let's look at some of the nomenclature, all right? So carboxylic acids, we need to remember that we count the carbon in the carbonyl group, all right? So we're looking at this type of carbonyl compound. So if N is 0, all right, we're looking at this, right? So if we don't have any other constituent group, we have what is called formic acid or methanoic acid. It's the acid that causes your skin to burn when ants sting you, right? So ants actually don't sting or bite, they spray methanoic acid onto your skin, right? So when they do that, it burns through the skin, it makes the irritating reaction, right? So that's formic acid there. We have acetic acid, ethanoic acid, right? That is vinegar. So a solution of ethanoic acid is what we use to make vinegar, right? We have propanoic acid as well, and butyric or butanoic acid. So it's just going up by numbers, right? Keeping in mind the carbon, the number of carbons. All right? Okay. So let's continue. The carboxylic acid group is polarized. So we know that there are electronegative elements on the compound, right? So the most electronegative element in the carboxyl group will be oxygen, all right? So oxygen is the most electronegative, right? Circling the oxygen in the molecule. That means that electrons are going to be moving closer to it. Electronegativity is the tendency for electrons to move closer, right, towards the itself, right? So it creates two poles, right? It creates one dipole going so, and one dipole going so, all right? So two dipoles, so it's extremely polar, all right? The slightly positive carbon is very, very, very vulnerable to nucleophilic attack, right? And the slightly negative oxygen is very, very vulnerable to a electrophilic attack. All right. So keep that in mind. So the hydrogen atoms also is very easily lost. And this is why it's an acid. So we remember Le Chatelier's principle. Remember chemical equilibrium. Remember acid equilibrium. All them something there. Unit 1 chemistry. Beautiful. All right. So since you guys remember all of that, this shouldn't be much of a problem, especially when we start looking at acidity and basicity of organic compounds, right? So let's look at this now. Remember, if there are any questions, stop me in my tracks and we'll go through it. Okay? Physical properties. We know that it's very polar. We looked already at the fact that it's very polar. It has two dipoles. Most molecules only have one, right? But in this case, what we're looking at, we have two dipoles. So obviously, the first physical property would be that it is a very polar compound, right? It can form hydrogen bonds to one another, and to water, all right? So it can form hydrogen bonds with itself, all right, with other molecules of its kind, and hydrogen bonds with water. So that means that it can be dissolved, right, in an aqueous solution, or it can be seen as liquids, right, when hydrogen bonded to each other. They boil at higher temperatures than aldehydes, ketones, and alcohols, right? So they're less volatile, right? Smaller carboxylic acids are soluble in water. Lower molecular weight acids have sharp and sour tastes and unpleasant aromas, right? So you have ethanoic acid. Vinegar does not have a nice odor. Vinegar is a low molecular weight acid. So it has a sharp, sour taste and an unpleasant aroma. But some acids have nice aromas, such as citric acid, right? It's where it's all citrus fruits have citric acid. We have tartaric acid, which is present within what are those fruits called again? Tamarind. Tamarind has a high concentration of tartaric acid as well as grapes, right? So some of those larger acids have another type of associated flavor with them. That's because it's associated with the esters, right? But we're going to talk about esters, right? Longer chain carboxylic acids are called fatty acids, right? I'm going to be looking at them and are important components of biological membranes. Okay. So let's look at this now. The chemical properties now. We know that ethanoic acid is a weak monoprotic acid, meaning only one hydrogen ion can be created, right? It's monoprotic. Let's look at ethanoic acid, right? I don't know why my pen isn't writing, Guys, my pen not writing. Guys, my pen not okay. So I'm not sure why the pen is not writing now, guys. Okay, so the pen is writing now. So hydrogen, my pen not writing. Okay, let's go. So we have this right here. It's monoprotic, meaning that it can only release this. Okay, give me one moment, guys. One moment. Okay, so as I said, it's monoprotic. It can only create one hydrogen ion, right? So it's acids like these partially dissociate in water as well. And what do you know about acids that have partial dissociation? What do we know about acids that display partial dissociation? Okay, so I'm going to ask the question again. What do we know about acids that have partial dissociation?
They are classified as weak acid.
Lovely. All right. So they're weak acids. Okay. So they're weak acids. We know that. Organic acids are weak acids. Love that. All right. So they turn moist blue litmus red. We know that already. And they react slowly with metals, bases, and carbonates. Okay. So let's look at some of these now. The reactions with sodium hydroxide. We know that sodium hydroxide is an alkali. Right. So the salts of carboxylic acids are known as carboxylates. Right. So we're going to name our carboxylates properly. Right. So let's look at this now. We're looking at sodium methanoate, right, specifically, and sodium ethanoate, right? So just using it as an example for us to know how to name them, right? So if it only has a methyl group 1 carbon, it is a methanoate. If it has 2 carbon, ethanoate, right? 3 propanoate, going on and on and on. And those are the carboxylates. That's how you name carboxylates, right? So let's look at this now. Propanoic acid now reacts with sodium hydroxide to give sodium propanoate and the water. So we know that the hydrogen and the hydroxide go to create water, right? And then the sodium goes into the negative oxygen that is left on it, all right? Hopefully you guys can see this. When this leaves, we're going to be a negative oxygen that this sodium can attach to, and then the hydroxyl leaves to form water, okay? You don't look at mechanisms right here that much, by the way, but it's really easy, so you can figure it out actually, right? So we have an acid and an alkali gives us a carboxylate and water. Make sense? Make sense, guys? Organic acid and alkali gives us a carboxylate and water. Make sense? It's literally a salt and water. Same thing, but I say carboxylate and water for to know that we're talking about organic salts. Okay? So we have an organic salt and water. Go ahead.
Yes, sir. That's good.
Lovely. Reactions with metals now. Carboxylic acids react with sodium to form sodium metal and hydrogen gas. Same thing like our regular acids, inorganic acids react, right? So other reactive metals also form salts. So let's, for example, look at magnesium methanoate. That is one structure that we could have, right? So in this case, we have an acid, right? It's an R group, so we don't know, right, what type of acid it generally is, right? So we just know it's a carboxylic acid reacting with sodium to give sodium carboxylate and hydrogen gas, right? And how would we know that it's hydrogen gas being released? How would we know? We put the carboxylate into a solution. Well, we have a carboxylic acid solution. We add our sodium, and we have a gas being produced through effervescence, right? So after the solution effervesces, how do we know that it's hydrogen gas?
We put a lighted split there, and if it goes out the squeaky pop, then we can confirm that it's hydrogen.
Lovely. All right, hydrogen is explosive in a sense. All right, so it should go with a squeaky pop. Lovely. All right, so that's fine. That's fine. Okay. Reactions with hydrogen carbonates and the carbonates. So carboxylic acid would react with carbonates and hydrogen carbonates to form a carboxylate salt, water, and carbon dioxide. So in this case, we have ethanoic acid and sodium hydrogen carbonate, and we see the creation of sodium methanoate, right, carbon dioxide and water. Make sense? I don't want you guys to look, you guys must see the equations, right? Because at the end of the day, it's not more than this. All right, it's just equations we're looking at, just to remember them, right? Any issues?
No, sir.
All right. Reactions of carboxylic acids with alcohols now. Carboxylic acids react with alcohols in the presence of an acid catalyst, which is usually sulfuric acid, right? The reactants are heated under reflux to prevent the loss of volatile alcohols and esters, right? So we don't want alcohols to be evolved, right? And we don't want the ester to escape, right? So the esters are distilled off when the reaction is complete. This type of reaction is called an esterification, right? So when alcohols react with acids in the presence of concentrated sulfuric acid, right, under reflux, then you'll get an O8, right, which is an ester in this case, right, and a water molecule, right? So ethanoic acid and ethanol gives you ethyl ethanoate, right? And remember, the ethyl is from the alcohol. Remember this, we start with the alcohol name and then we end with the acid name. So it is ethyl ethanoate, right, and water. All right, so that is esterification, the creation of esters. All right, so remember, concentrated sulfuric acid, reflux. All right, looking at conditions and stuff like that. All right.
Sir, can you go over how you name it again, please?
Okay, so no, wait, we're gonna go over it, right? I'm not gonna go over it right now, but we're looking at reactions of esters after, and I'm going to actually look at ester nomenclature, right? So we're gonna go over that, right? Shouldn't be too much, okay? Just hang in there. So we have just a few more reactions looked at under the reactions of carboxylic acids, and they are our substitution reactions. All right. So the reactions with PCl5, right, PCl3, and SOCl2, right? So the carboxylic group is involved in substitution reactions as well. So the hydroxyl group, so let's draw the group itself, OH. This group will be substituted for a halide, and that will create acyl halides, right? So the OH group is replaced by an halogen to create an acyl halide, right? In this case, we have acid chlorides, or acyl chlorides, right? That's what the syllabus asks us to look at. But if they give us something like fluorine or bromine, we know we can create acyl bromides, acyl iodides, acyl fluorides, right? But acyl chlorides are the most common, so we just look at acyl chloride specifically, right? So acid fumes of HCl or HBr can be produced, and this is why we must do this under a fume hood. All right. So if you plan to do this in the lab, right, and you don't do this without a fume hood, I'm not sure who will be scheduling a funeral, but it will have to be scheduled. Right? So we need to keep that in mind that these organic chemistry reactions, organic chemistry is no joke, right? Everything in the lab, assume that everything in the lab can kill you, right? And you use the correct precautionary measures. Okay? So PCl5, right, reacting with an acid, organic acid, will give us the acyl halide. So notice that the acyl halide is always produced. But with PCl5, we have the creation of POCl3 and HCl. Note that. With PCl3, we have the creation of phosphoric acid. Note that. These are just things that we just have to remember. We don't have to know the mechanism. We don't care about the mechanism. Neither do we want to understand the mechanism. We just need to know what is produced, right? With the thionyl chloride, we have the creation of sulfur dioxide and HCl gas. All right, are there any questions? Any questions, any concerns? Guys, please tell me if there are any issues. Are there any issues at all?
No, sir.
Are you sure?
Yes, since you just have to just know it. Can look over it anytime.
All right, lovely. All right. So we just have to know what is produced. I remember that you must do this under fume hood, This is why I put fume hood here, Must do these substitution reactions under fume hood. That is something that the syllabus explicitly states that I must tell you. Right? But specifically PCl3 must be used on a fume hood, right? So like PCl3 specifically, they hinted to that, right? But using these type of reactions, looking at these type of substitution reactions that produce acid fumes, I recommend that all of them are done under fume hood. Okay? Unless you want your eyes to burn and your nostrils to burn and your mouth to burn, right? Unless you want all of that happening, right? It's going to feel like when you're cutting onions and the onion juice goes in your face, because we know that onions have sulfurous compounds, and when they touch your eyes and stuff like that, it turns into sulfuric acid and it just starts to burn. So that's why onions burn. But it's similar to that. It's gonna give a similar feeling to that, but kind of worse because this is like pure HCl, right? So stuff like that, right? So practice question. So describe using equations, reactions of propanoic acid with the following. So I want you guys to try this. Just take them down right now, please. And I want you to try it, and then I'll check my WhatsApp and see what your responses are. If you want to check your responses with me, you guys can send me the answers to these questions. If not, then it's fine. All right? Okay. So the key points. Could somebody do the honors? Could somebody just read the key points, please? Who would like to do the honors? If you read it, it solidifies a little bit more. Anyone? Laquanda, would like to go?
Sure.
Right.
Okay, so carboxylic acids are weak monoprotic acids. Hence, in a reaction, the equilibrium lies to the left, formation of reactants. 2. Carboxylic acids react with sodium hydroxide to form a salt, and water with sodium hydrogen carbonate to form a salt, and carbon dioxide and water. 3. Carboxylic acids react with reactive metals to form a salt and hydrogen. 4. Carboxylic acids react with alcohols to form esters. And 5. Carboxylic acids react with PCl5, PCl3, and SOCl2 to form acid chlorides and hydrogen chlorides.
Lovely, right? So those are the key points behind all of this, right? Thank you so much. So it's just that. We're looking at physical properties, chemical properties, sodium hydroxide, reactions with sodium hydroxide rather, reactions with reactive metals. So we're talking about group 1 and group 2 metals. We're talking about the alkali metals and the alkali earth metals. Please note that those are the reactive metals we're talking about. Mostly, right? So mostly you'll see that in unit 2, right? Reactions with carbonates, hydrogen carbonates, reactions with alcohols, and then we look at the substitution reactions with phosphorus 3 chloride, phosphorus 5 chloride, and thionyl chloride. All right. So we have that there. And the reason why we have 3 and 5 is in the name is because of the oxidation states. So please don't forget that. All right. So the oxidation state of phosphorus in PCl3 should be what? 3? Positive 3. And the oxidation state of PCl5 should be positive 5. Right? Because chlorine is going to be negative 1 in these compounds, right? But I won't insult anyone's intelligence because I know that you guys mastered unit 1 already and you know your oxidation states. Alright? So just a brief reminder. Okay? That is reactions of carboxylic acids.